we are recording. Let me start with the compactness again, so that we record this part. So we want to define the concept of compactness. So given a set A, a subset of X, we will introduce the notion of a cover. A cover, see if this is this red one is the set A. A cover of A is some set, collection of sets A lambda such that the intersection of all them contains A. So here you have one. You have all these yellow lambdas and they cover this set A. And this lambda here can be a finite number, infinite number, discrete number of sets, or it can be a continuous, anything. And what we will say is that this is then a cover. And a subcover is some subset of this cover. So you take some of these A lambda, not all of them. And that's a subcover. And then the compactness is the following. So you get an A, a subset of X, and you say this is compact if given any collection A lambda of open sets that cover A, there exists a finite subcollection of these that also cover A. So there is always a finite cover. Given, so you give me the collection and I find a finite collection, right? So you give me the cover and I have to find a finite collection and I have to do it for everyone. So it's not that you just gave me one and I find one cover and I find a subcover. It's for everyone. So let's see some examples. So let's X be an infinite set of points in the discrete topology. So in the discrete topology, remember, every point is an open set. Then a cover of X consists of all subsets of the form X with X belonging to X. Because every X is open in this case. And so for this cover there will be no finite number of them that will also cover X, because we say that X has an infinite number. So therefore X is not compact. On the other hand, if X has a finite number of elements, then it will be compact in any topology in this case, because with the number of open sets that you need will be always finite. On the other hand, if you have X to have the indiscrete topology, that is only phi, the vacuum, and X are the elements, then X is always compact. Why? Because there are only two elements to do the cover, so every cover is finite. So these are the extreme cases and not really important. So let's go to some more intuitive notion of compactness. Suppose you take the open interval 0, 1 in the line. And we say that this set is not compact. Why? Because, for instance, we can take this subcover, An to be 1 over n, n minus 1 over n. So these are sets that are like this, and they are approaching this side, right? And from this, no finite cover will cover 0, 1. But the whole set is going to cover it. So this set is not compact. On the other hand, if you close it, then you can find, if in both sides, then you can see that the 0, 1 is compact. The 0, 1 closed. So let me this like that. The set that contains both the 0 and the 1. That's compact. And you can prove it, and this, in fact, is one of the exercises you can do. So this is a notion of compactness. It's very strange because you say, okay, to prove that something is compact seems to be very difficult because you have to look at all the possible collection of covers, and for each one of them find a finite subcover, which is sort of difficult to handle. But nevertheless, is in fact the way of handling compacts, the compact notion is okay. And here we have the big theorem on this. So let's X and Y be two topological space, and phi a map from X to Y which is continuous. Then if A is compact in X, then phi of A is compact in Y. So you have X and Y, and if you have a compact set here, the image by this map, a continuous map, is also compact. Of course, it's compact in the topology of Y. So let's see if we can show it, this theorem, so that we get some idea of how to deal with the compactness concept. So let's start with O lambda be a collection of open sets in Y that cover phi of A. So we get some collection here that covers it, right? So these are open sets in Y. And since they are open set in Y, when I send them back with the map, when we do phi to the minus 1 of these O lambdas, these one are open, right? So what do we get when we go back is some set some open sets here, and they also cover A. This was what we call A, with red. They also cover A, because we said when we send this side we got this, so the phi to the minus 1 has to contain all the A. So they are also cover A. But we know that here there is a subcover because this A is compact. So we have a finite subcover here, and then we send this subcover to this side again, and we see that this subcover, this finite subcover, also covers this. So the image of A is also compact. And since this argument is true for any cover, we see that this is compact. Is it clear? So you see how the the continuity confabulates with the compactness to get this theorem very easily. So the continuity goes from here to here with the inverse, with the pre-image, while the compactness goes this way. So if this is compact, this is compact. And we have an application of this. I suppose you have any x, and we have any a here. A could be the whole x, right? No, there is no problem with that. Any a that is compact, and we have a map which is continuous here into the real line. So the y is a real line. Then this set is compact, so here the image of this map phi of A is also compact. I say it like a segment, but could be anything, right? Could be several segments, etc. So since this is compact, we know that the maximum and the minimum of all these values that can take are going to be here, right? They cannot escape the compact set. So this function is going to attain its maximum and its minimum in this set, in A. So we know that there exists a maximum of phi of A and a minimum. There are values. This is phi of x plus in A. And this is some value phi of minus with x minus in A. Right? And so this is what we usually use to say that the maximum and minimum are obtained. And this is valid when the map is continuous and the set where the map is defined is the set is compact in this sense. So this theorem always is valid when something is compact in the appropriate topology. So we see that we need topologies all over the place, and we need compactness. And most of the problem in infinite dimensions is that usually the things you think they should be compact, like a ball, so some vectors of norm less or equal to 1, they are not compact in infinite dimensions, so you have problems with this. Something that is very common in finite dimensions, in infinite dimensions you lose. Are okay up to the moment? There are questions? No questions? So for the next, there is another application of compact sets, and this has to do with accumulation points and limit points. So let me introduce the concept. So first we have to introduce the concept of sequence. A sequence in a set X is a sequence. It's a map from the naturals to the point x, so that we have for every number a value. So you have an infinite, the image of n by this map is an infinite set of, so a sequence is like that. It's an infinite number of elements of x. And we say that this sequence has a limit point see if so we have, say, we have a sequence and we say x1, say x2, xn, and we say that this sequence has this limit point if given any, let's change color, any open set here, after for n there exists an m such that for all n bigger than this n, the xn's are inside O. So given any open set around containing the point, we can you can use neighborhoods here if you want, because in any case the content opens. So it's a limit. This sequence has a limit point, x is a limit point. If given any open set containing x, there exists an n such that for all n bigger than this, the sequence stays here. So after a while, the sequence is inside here. It's approaching in some sense. So this is a limit point, and then we have accumulation points. So this is limit. An accumulation point is a point such that x, such that given a neighborhood, any neighborhood of this point, infinite many points get inside here. So that it could happen, for instance, that the sequence comes here, enter this region, goes out, comes here, enter again, goes out, and so on. But have to visit the region more and more. And arbitrarily close, because I can take smaller and smaller neighborhoods and get this to be smaller. If the topology have many neighborhoods. If it doesn't, then you don't have. And we're used to think of, okay, I have a sequence and then I have a limit point. And this limit point is unique. That's what you think, okay, because we're approaching this point, and so we are closer and closer. So if we are closer to this point, maybe we cannot be closer to this point. But let me show you an example that this is not true. And so, just to show you what can happen. For instance, let's look at this space. So this is open up to here, say this is the real line, x less than 0. And here we take two positive half lines. So we have 2 points here and the lines. So this is a set x. These are x bigger than 0, but we have 2. And this is a set, right? And I'll give you a topology. Here the topology is that this is an open set, this is an open set, this one, etc. This is an open set, this is an open set. So there are open sets that comes here and continue here and here. And if you check, this is a topology. So this collection of open sets, if you take all the intersections and all the unions, all the finite intersections and all the unions, they form a topology. But notice that if I have a sequence coming here, approaching 0, then this is a limit point, and this is also a limit point. So we can have things like that. This is because this topology is not separable, meaning that these 2 points, I cannot find a neighborhood of this point a neighborhood of, say, of this point, which is disjoint from the neighborhood of this point. So this is what is called a non-Hausdorff. I think one of these is either the S or the FR space. Topological space. So you can have slaves. So be careful with that. And here there is a theorem which is very important in many applications that says let A be compact, then every sequence in A has an accumulation point. So if we have a compact set, so if we have X, and inside X we have A, and we have a sequence that is inside A, so the map sequence of n is contained in A, or at least for big enough n, then this has an accumulation point. So a point is visited every now and then, at least. And this you prove, it's very easy to prove this, but it's a very strong result. So let's assume, contrary to the theorem, we are going to prove it by reduction to the absurdum, that there exists a sequence xn in A without any accumulation point. That means that given any point x at A, there will exist a neighborhood phi of x, Ox, containing x, and a number nx, such that if n is bigger than nx, then xn is no longer here. So that will tell me that this point xn is this point x is not an accumulation point. And since we don't have any accumulation point, this should be valid for any x in A. So the collection of open sets, of these open sets, is a cover, it's an open cover of A. But A is compact, and therefore from all this, we can have a finite subcover that also covers A. So let me draw this here. We have this A around any point x. We take one of these, another point, we take this, etc., and then we cover. And we know that around each one of them, after a while, there is no more, the sequence is not entering here, right? But we know that we can cover with a finite number, right? So we cover it with a finite number. say. But then if we cover with a finite number, that there will be a number n, which is the maximum of all the nxi of the finite subcavern. So this nxi is the last number for which the sequence enters this neighborhood, this open set, such that since they are finite, there will be a maximum of that, and this number implies that the sequence after n is not there entering any longer A, but the sequence is in A, so there should have values here. So this is an absurd. This is false. Huh? So there should be an accumulation point. Basically, the idea is if something is compact, you start putting points and points and points. There is a moment where, given any neighborhood, I have to go inside some of these neighborhoods again and again and again and again when I do it smaller. Right? Is it clear? Questions? No? Okay. So these two things we are going to use extensively. Now we are going to switch a bit of topics and talk about completeness of metric spaces and Cauchy sequence. Right? So we take a metric space is a space, we defined the other day metric spaces. It's a space where we have a notion of a distance between points. This is a map from x cross x to the negative line, such that dx on y is the same as dy of x, dx x is 0, and we have a triangular inequality, dx y is less or equal to dx z plus y z. So this is a distance. This notion is the distance between x and y. And assume that we have a sequence xn which is converging to x, namely that the distance between x and x goes to 0. So once we have a metric space, we have a topology given by this distance, and so we can talk about convergence, and we say, okay, this sequence converges to this point if this distance goes to 0. What that means is that given any epsilon bigger than 0, there will exist an n such that the distance between xn and x is less than epsilon for all n bigger than n. That we are getting into these neighborhoods. So we have an epsilon here, and when the sequence enters this distance, gets closer to a distant epsilon, it's inside here, right? And once it enters, it stays for after a while. But now notice this: if we have this sequence, then we can use this triangular inequality to do the following. We take two members of the sequence, xn, xm, look at the distance between them, and this is less than the distance between xn and x and xn. And this is less than 2 epsilon. So what we see here is that if the sequence converges, then the distance between the members, so this is true for all n bigger than n. Then the distance between the members of the sequence has to go to 0. The sequences where this happens, when this distance goes to 0, are the Cauchy sequences, are called Cauchy. So a sequence is Cauchy if given epsilon bigger than 0, there exists n such that d of xn smaller than epsilon for all n bigger than n, right? So this is a sequence, a Cauchy sequence. It's a Cauchy, it's a sequence where the distance between points goes to 0. We are going to use a log this, but instead of a distance, which is a distance actually, we are going to take norms. So we are going to have things like that in vector spaces, where we have norms, but it's more general. So this is a notion of a Cauchy sequence. And so the question is, okay, if we have a Cauchy sequence so that the points are getting together closer and closer, does there exist a limit point? That is an x such that the distance between x and xn goes to 0. And the answer, the quick answer is no. Suppose you take the real line, subtract the 0, so we have a here like that, and we have the sequence 1 over n. This sequence is getting smaller, right? If we take the difference between this goes to 0. Nevertheless, the point is not there because 1 over n will like to converge to 0, but I took out 0. So it's not converging to any element of my space x. Right? So this in general is not true. And so, but in a way, for instance, if you are, you might say, okay, but if I am in a vector space, I cannot subtract a number of a vector space, right? Because then it will be no longer a vector space, because if I do b minus b, will be 0, and I took out 0, right? So that wouldn't be possible. You cannot subtract a number. But nevertheless, there are many spaces, so we are going to see several later on, which are not complete. They which have this property that there are sequences that are Cauchy, nevertheless they are not converging to anything. So we have a notion here. We say X is complete. Let's put the X. So a metric space is complete. If every Cauchy sequence has an accumulation point, has a limit point. Okay? So this is the notion of completeness. And this is going to play a big role in what follows. So we can make with this I finish everything on topology, and we are going to start now with infinite dimensional spaces, functional analysis. So let me stop now and rest for a while, and we can start at 5 past 10. We put a formula there in the chat. Please fill it with your name. This is to have the assistant requirement fulfilled. Okay, so we stop until 5 past 10.